Okay, so we're going to talk today about the Lorenz equations, which are a 3D system, which means there's three first order ODEs. And so these equations came out of actually studying atmospheric dynamics and convection rolls in the atmosphere and things like that. So these are not specifically physics. Well, I mean, they're physics equations. They're not mechanics equations, right? So these equations aren't related directly to throwing a ball in the air type of thing. So the dynamics in the Lorenz equations are the dynamics of some variables that come from atmospheric physics. So the equations themselves are x dot is sigma times y minus x. Y dot is rx minus y minus xz. And z dot is xy minus bz with parameters sigma, r, and b are positive numbers. And then, x, y, and z are our coordinates. And one thing to notice here is that there's really not a lot of nonlinearity. These are nonlinear because we have an x times a y and an x times a z, right? So there's a nonlinear term here and there's a nonlinear term there. And everything else is pretty darn linear. I mean, this is not a particularly crazy looking nonlinear system. But, okay, so it has some nonlinearity to it. There's products of x and y and x and z. Now, at the beginning of the class, we studied, so the first couple of lectures in this semester, we studied Hamiltonian flow. And we had the Louisville theorem, which said that the Hamiltonian flow preserves volume in the phase space. And what we're going to see in the Lorenz equations is that they very much do not, right? So the Lorenz equations are not Hamiltonian flow. In fact, they have a strong volume contraction. And it's worth understanding and proving that there's a volume contraction, right? So, so the volume under the flow of any region in phase space is going to go to zero, which is really kind of critical, right? So the trajectories don't end up winding around a region of three-dimensional space. So we got a three-dimensional flow, right? You run the system for a while and the trajectory is not filling a three-dimensional volume somewhere in the space because there's this volume contraction. So let's try to understand how you would prove a volume contraction. So let's suppose that you've got some volume at some time t, and there's some boundary to this volume. So V at t is some enclosed volume with some surface S of t. We're going to define n hat to be the normal to the surface, right? And then we're going to say that x vector dot is some f vector of x. And so f vector is the flow. Okay. So f vector are these equations, right? So we're basically saying that those are the Lorenz equations. I'm just going to tighten them down into one thing. Good? Okay.
Yep.
So now, so the idea that we're going to have is that if this is S at t, and everywhere on the surface there's some flow vector, then f times dt moves the surface out a little bit to S at t plus dt. Right, so we got every point basically on the surface has gotten moved outwards some amount. Okay. Sound good?
Yep.
Okay. So now, I'm going to say, I want to find out, for instance, some volume. So this has nothing to do necessarily with Lorenz equations. What I'm basically trying to do is try to derive, given that I have a flow, how much my volume changed in some amount of time, right? So this added volume is going to have some sort of, dA on the top. Oops. Right, so let's suppose I have a little piece of it here, right? This is my little three-dimensional piece, right? And the height here is f dot n hat dt. So how much you bump out. So f dot n hat is the extent that the flow was perpendicular to the surface. And so the volume at t plus dt is going to be the volume at t plus the integral over the surface of f dot n hat dt dA. So if dA is the volume element on this black surface, then if the flow is pushing me out away from the surface, I rise a height F dot n hat dt off of the surface. That makes sense?
Yep.
But now this quantity here is the flux of F through the surface S, right? So remember, if I had the electric field dotted into the normal vector, the times dA would be the flux of the electric field through the surface. So if I move this business over here and I move the dt over, I would have that V at t plus dt minus V at t all over dt is the integral over the surface of F dot n hat dA. So that's my flux. Okay. And then if I take the limit as dt goes to 0 of V at t plus dt minus V at t over dt, that would be V dot. So this capital V is my volume, right? So V dot is now the integral over the surface of F dot dA. And it's a closed surface, right? So I'm going to do this over some closed surface. Right, so I've just applied a derivative definition.
Right.
Good.
Yep.
Okay, and now, so I've got V dot is the integral of F dot dA over the surface, but if I employ the divergence theorem, that's the integral of the divergence of F dV over the volume. So everything that I've done up to this point is true for any flow. I haven't used the fact that this is the Lorenz flow that I'm interested in. Okay, good.
Yep.
So the Lorenz flow, x vector dot was F vector is x dot is sigma y minus x, y dot is rx minus y minus xz, and z dot is xy minus bz. So if I go to take the divergence of F, I would need to take d by dx of sigma times y minus x plus d by dy of rx minus y minus xz plus d by dz of xy minus bz. Right, the divergence is the x derivative of the x component, the y derivative of the y component, the z derivative of the z component. And so the divergence of F is minus sigma for the x component derivative, minus 1 when I do the y derivative, minus b. But I said at the beginning that I was only interested in R, sigma, and B being positive numbers. So that means that the divergence of F is negative everywhere. Okay, and in fact, it's constant. Right, here's another thing to say about, right? I mean, when I took the divergence of F, I didn't just get a negative number, I've got a constant number. So I had before that V dot was equal to the divergence of F dV. Well, apparently it's equal to minus sigma minus 1 minus B times the integral of dV. So apparently V dot is equal to minus sigma minus 1 minus B times V. And that's just a linear first order ODE. Right, so the solution to a linear first order ODE is a real exponential. And I'll factor the minus sign out. And so I see that the volume goes to 0 exponentially fast. So whatever I start with, I end up with 0 volume in my flow. So if I have X, Y, Z, and I start with some ball here, and I integrate all of the points of the ball that are inside that ball forward in time. So all those points are different starting places in the trajectory. I integrate all those different places forwards in time. The amount of space that that ball occupies later has 0 volume, exponentially fast. So if I start a bunch of rays in the Lorenz equations, and a ball of volume V0, and I flow them forward, the ball volume goes to 0 really fast. Okay, so good so far?
Yeah, this makes sense.
Okay, so now there's a number called RH given by sigma times sigma plus B plus 3 divided by sigma minus B minus 1. And if R is less than RH, then there are I think 2, right? 2 stable fixed points. Actually, I'm just going to say there are stable fixed points because I think there's a bifurcation that happens. I'm pretty sure there's a pitchfork bifurcation where you start with one stable fixed point, and then as you change your sigma and B parameters, you end up with 2 stable fixed points and 1 unstable fixed point. And so the reason, so if I'm in this low R range, So in the low R range, the flow goes to some stable nodes. And so that's why the volume goes to 0. Okay, so it makes sense that if I have volume going to 0, that one explanation of why the volume can go to 0 is that all of the flow runs into some stable nodes. Sort of the standard thing you would expect, right? But if R is greater than RH, the volume still goes to 0, but there are no stable nodes. So how is it that you can have a volume in a three-dimensional space go to 0 without all the points going to points on a stable node? And the answer is that all the points start to fall on the strange attractor. So this is a new type of structure that shows up in nonlinear systems of 3 dimensions or more, right? There are not strange attractors in 2-dimensional systems, no matter how nonlinear they are. But here we have a 3-dimensional system that's nonlinear. And so this strange attractor is a surface. And that surface has no volume, but it's not 2-dimensional. And so if you have seen the pictures of your standard strange attractor, so things are going to come along here and it'll zip around here for a while, and then come over here and zip around here for a while, and come around here and go back and forth, right?
Yep, I recall this.
So the issue is that in 2D, your flow lines can't cross, which is our statement of the existence of solutions to a 2D ODE. So if you're constrained to the plane of the page, right, and you go over this way and you start to circle back, you can't run back into your flow line that you were on, because if you did, that point that you were at, you would be at the same physical place going in 2 different directions, and then you wouldn't have uniqueness in your differential equation solution. So if you get over here, you got to come back, you got to bounce off of it somehow. So you could wind around, but whatever you do, you can't cross over yourself in 2 dimensions. But when you look at the attractor for the Lorenz attractor, it's on one side, and then it passes over to the other side, and then it passes back over to the first side, and it passes back over to the second side. And so if you look at it carefully, in order to pass from one side back to the other side, it has to pass just behind a place that it's been before. So on these swings from left to right, it's just infinitesimally behind the place that it was before. Okay? So now, the fact that it's crossing back and forth means that it cannot be, the attractor that you're landing on cannot have 2 dimensions. So the attractor here cannot be two-dimensional because it's passing back and forth on itself, right? If it was two-dimensional, then you would run into existence and uniqueness problems for the differential equation, but it doesn't have existence and uniqueness problems. So the attractor itself cannot be two-dimensional, which is okay, fine. So the attractor is not two-dimensional, but we just proved that the volume is going to zero. So the attractor cannot be two-dimensional, but the volume of the points on the attractor is zero. So the attractor itself has more dimensions than two, but it has less dimensions than three. A set of points that has a volume, in order for a set of points to have a volume, that set of points must lie in three dimensions, or put another way, right? In order for a set of points to have three dimensions, those points must span out a volume, right? So sort of think about your standard integer dimensions. So standard integer dimensions. If you take any collection of points that are somehow separated from one another, they have a dimension of zero, no matter how many of them you have. So, for instance, the set of all integers. The set of all integers, there's an infinite number of them. But if you ask how much room do they take up on the number line, the answer is zero. They don't take up any room on the number line. Good?
Yeah, that makes sense.
Okay. So something that has dimension zero has no length on the line. So if you have a dimension of one, this is a collection of that somehow has length. A dimension of two are points that have area, and a dimension of three, of course, has volume.
Does it depend how you arrange the points? And
Yes.
that's what gives your dimensionhood, right?
Right. So there's
Okay.
all sorts of points. So there's actually, one of the things that's fun in here, or this would be something else that we could talk about, is there's all sorts of sets which are dense, but still dimension of zero. So what do we mean by dense? So dense means that for every point that you pick in the set, any interval you pick on the line has another point that's in the set. Okay, so let us think about the integers. right? So here's my number line. And here's -1, here's 0, here's 1, here's 2, here's 3, here's 4, here's -2, right? So that I'm thinking about the integers, right?
Yep.
So the integers, for instance, are not dense. And by that I mean, I can create an open interval that contains one integer and no others, right? So I mean, if I just do that, I can isolate 2 from 3. All right. So the integers are not dense. So they have dimension of 0. Okay. They have dimension of 0 and they are not dense. Okay. On the other hand, you can do some funky things. One of the most fun thing you can do is examine things called Cantor sets. Okay, so we have something called the middle thirds Cantor set. So you start with the interval zero to 1. Right, so you start with this line that's of 0 to 1. And you start by taking out the middle third. Okay.
All right.
And then you take the middle third out of each of those. And then you take the middle third out of each of those. And then you take the middle third out of each of those. Okay, so you keep doing that until you get down to a set of points.
So that's where each like interval becomes one distinct point
Yeah.
in your set. Okay.
Yep. Now, the thing about the middle thirds Cantor set is that it is still dense. But it has no length. So the middle thirds Cantor set has more points in it than the integers. But doesn't occupy any length. I mean, you look at it, it clearly doesn't occupy a length. But it has more dimensionality than 0.
And to be clear, when we started with just the interval of 0 to 1, did that occupy the first dimension or no?
Yeah, so that
It did because it had
this
points.
is, yeah, this step
That's easy.
has dimension
Yep.
1. So does this step.
Yep.
In fact, all of these have dimension 1 until you go to
Right.
infinity.
Because then you're at points which
Then you're
don't
at
occupy
points.
a length.
Right. So
Okay.
you've lost all your length when you take this all the way down to infinity, right? So now you're at points. So you don't have dimension 1 anymore. But
Right.
you also don't have dimension 0. So our standard definition of dimension in terms of length, area, and volume works for integer dimension concepts. But it doesn't work for all possible sets. So for instance, the strange attractor that we have has no volume. So it is not of dimension 3. But it cannot be of dimension 2 either, because it couldn't cross back and forth. It was of dimension 2. So the attractor that is associated with the Lorenz system has to have some dimension between 2 and 3. And so what we need to do is come up with new definitions of dimension, which reproduce integer dimension when that's the right dimension, but have other values that are between the integer values for other types of sets or constructions.
Is this done with the limits of a generalization of volume or something like that?
Yeah, so there's a
Okay.
couple of ways to do it. One is called box dimension, and one is called similarity dimension. There's a bunch of different definitions for these.
Okay.
Here, I guess I can try. We've got
This
time.
was just in the book that I had mentioned before the class, and I recalled it. So yeah, the equation I'm looking at is like the natural log of r over the natural log of some generalization of volume or something like that.
Yeah, right. So there's right. Yes. It's the number of times it repeats divided by the number of times that you shrunk it by, I think is the box dimension.
Okay.
Oh,
okay.
So that's one of them. There's another one called the similarity dimension. So let's see if we can do this game. So if we do the what is the thing that I'm trying to build? The Koch, yeah, the von Koch curve. Okay, so another one of these is to build something called the von Koch curve. So in the von Koch curve, you start with the line, and the line has a length of L. And then you take out the middle of the line and you add ends of it so that all of these have length of L. So and then you go, actually not L. No, they won't have a length of L. And then you go into the third. Oh no, right. That's not what you do. Right. So you go into the middle third. Okay, 1, 2, 3. 1, 2, 3. Trying to do this right. And you draw something with where this is L over 3, this is L over 3, this is L over 3, and this is L over 3. That makes sense? So you take the middle part out, the middle third of it out, and you put it on these two other sides. Make a triangle out of it, okay? Good?
Yep.
And then you go to each one of these sides and you play the same game. So now you go this way, that way, that way, that way. This way, that way, that way, that way. This way, that way, that way, that way. This way, that way, that way, that way.
Oh, I kind of see. Okay.
Okay. So you go to each piece each straight line segment, in each step, you go to each straight line segment, you erase the third in the middle, and you make a little triangle there that has that length on it.
Yep.
Okay. And then you keep going, right? So then you got, line dot 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 dot. This is going to now have one of these on it. This one's now going to have one of these on it. This one's now going to have one of these on it. This one's now going to have one of these on it. This one's not going to have one of these on it.
It looks like a giant snowflake.
Yeah, and so you get this thing.
It is some sort of a tracture, right?
Right. So this is another fractal type of thing, right?
Okay.
And so we're getting to the word, what do we mean by a fractal? So something that's a fractal needs to be self-similar at all scales. So that's one definition of something that's fractal. And the other definition of something that's fractal is that the dimension is a fraction. That's not an integer. So if you think about, so you now ask the question, how long is this curve? Okay, so you ask, this von Koch curve that you built, right?
Yep.
Is it dimension 1? Well, no. Because its length is no longer finite. The length of the curve that you get becomes infinitely long because you can never bound how long the length is, right? So let's suppose that you say, so how do you know the length is not finite? Well, you would say, well, if I've done it 100 times, you could compute exactly what the length was at 100 times. Right? Well, okay, so its length is more than it's doing it 100 times. So if the length was finite, you would have to say, here's a number, and the length is less than that number. But any number you give me, I can just keep doing this curve, and I'll get something that's longer than that number.
And if you had a stopping point like that, it wouldn't be self-similar at all scales.
It wouldn't be self-similar at all scales. So the fact that you have to do this to infinity makes it self-similar at all scales.
Yep.
So its dimension is more than 1 because the length is no longer finite. But now the area is equal to 0. It's still kind of a line. Well, it's not a line, right? But it's something that has no area.
Because it doesn't enclose anything.
It doesn't enclose anything.
Yep.
Right?
But it obviously isn't a line.
So the dimension's got to be less than 2.
Yep.
But its dimension is more than 1. Hence, its dimension has to be some number between 0 or between 1 and 2. Okay, and so one way to define the dimensionality is to do the similarity dimension. And the way you define similarity dimension is, all right, where did I define similarity dimension in the book? The dimension is the natural log of m divided by the natural log of r, where m is the number of copies and r is the scale. So the idea is m, so something that has a nice similarity dimension scales by saying that m is r to the d power. Okay, so let's try to understand how that works. Right? So let's suppose that I take a box And then I take the same box and I divide it into quarters. The scale factor is 2. And the number of copies is 4. So if I take a square and I divide each side and I make it each halfway on each side, then I get 4 copies. If I take the same square and I divide it into something as third as big, I get 9 squares. So here, 9 is 3 squared. Here, 4 is 2 squared. So this thing has a dimension of 2. So something that has a dimension of 2, if you break it down into copies that are 1/5 as big, you'll have 25 of the parts.
Can you say that again?
Okay, so I took one square.
Yep.
I took each side and made them half as long.
Right.
So the scale factor is 2.
Yep.
I ended up with 4 copies. If I made each side 1/3 as long, I end up with 9 copies.
Yep. And 4.
2 squared is 4, 3 squared is 9. So M is R to the D, or if I flip it around, then D is the log of M over the log of R. Right, so if I start with, if I start here with M is R to the D, and I take the natural log of both sides, I have the natural log of M is equal to the natural log of R to the D, but that's equal to D natural log of R.
Yep.
Right. And so the dimension is the natural log of the number of copies divided by the natural log of how much you shrunk that thing. So if you shrink it by a factor of 3, you get 9 copies.
Okay.
Okay. So now if you do the von Koch curve, right? Then when you scale by a factor of 3, you get 4 copies. So if I start with just the line and I look at 1/3 the size, I have 4 copies. Right? So if you start with just the whole line and you make it 1/9 as long, and you count up how many line segments you have 16 of them. So the dimension is the log of the copies. The log of R is the log of 16 divided by the log of 9, which would also be the log of 4 divided by the log of 3, which is some number. I think the book works it out. Well, they just tell us that number. But it's more than 1.
It's a 1.26.
All right. So that's the similarity dimension of the von Koch curve. So once you start doing non-integer dimensions, so the different rules for dimensions have to agree on the integer ones.
Yeah.
But they might not agree, or they might not be well defined for a set that's something else.
So you can have different values based on.
So you can have different values, and you have to say which type of dimension it is, right? So the similarity dimension of the von Koch curve is the log of 4 over the log of 3.
Mm-hmm.
Okay. And then there's box dimension that works for some better than others and things like that, right? So these are our ideas of fractal dimensions and our ideas of self-similarity. So now getting back to our attractor idea, right? So the Lorenz attractor has to have some sort of fractal dimension. It's appropriate to say that the strange attractor of the Lorenz equation is a fractal in the sense that it has a non-integer dimension. It probably isn't correct to say it's a fractal in the sense that it has self-similarity at all scales, right? It's not really self-similar at all scales, but it's a strange attractor and has a fractional dimension between 2 and 3. Okay, that sort of makes sense.
Yeah, I'm interested in the fact that it isn't an attractor because it is obviously not self-similar, but it still has a lot of properties of a fractal.
Yes, it still has a lot of properties, right? So how much do they give us about the properties of the strange? All right, so this is a strange attractor. And there's maps of strange attractors.
Could it be that it's not defining a set?
Well, no, there's ways to do it. If you take Poincare sections, you end up with self-similar sets.
Mm-hmm.
Yeah, so this is nuts, right? So if you take the Lorenz attractor, so this is in the chapter on strange attractors in the book. I don't know if you bought the book. Did you buy the book?
I haven't, but I intend to.
Yeah.
I should have bought it earlier.
No, that's all right. So if you take the Lorenz attractor and you slice it, and you look at the points in which it intersects some slice.
All right, I'm with you.
And you lay those points next to each other, what you get is one of these Cantor sets.
Oh. Wow.
Which is just really nuts.
Cool. That's almost like the Mandelbrot set in the Feigenbaum attractor.
Yeah,
like
I mean, you get these things which are just nuts.
That's really strange. Okay.
Yeah. So there's these connections between these mathematics that you might go, why the hell is this here? So there is, so the self-similarity in the strange attractor for the Lorenz attractor isn't in the whole attractor. But if you take slices of it, those slices line up to Cantor sets, and therefore the different slices have some sort of self-similarity in the sense that the Cantor set is self-similar, because if you blow up any one of these little dots, you get a copy of the whole picture. Right? See, if I take the Cantor set here and I look at just this bit, and I just blew it up, I get the whole picture. If I looked at just this bit and I blew it up, I get the whole picture.
Right, okay.
right? So any one of these things that you pick up, if you zoom into it, you get the self-similarity back. So the strange attractor and the Lorenz attractor, even though it's winding around, when you do these Poincaré sections, which are just sort of cuts through them, give you these same sort of attractor things.
Wow.
Yeah, so there's a lot of really cool
makes
stuff.
It makes a set out of it. That's
Right, so
really
you can
cool.
make a set of discrete points
Yep.
out of where it passes through the screen. And then you look at those points and they end up falling on one of these Cantor sets.
Really cool.
Yeah.
It's just a conspiracy.
It's just a conspiracy. Anyway, so that's what I got for today. So I'm going to stop
That was really
recording.
fun.